This is the second section of the matrix algebra chapter, and here we're going to be looking at reducing matrices to diagonal form. So the first thing we need to understand is, what is diagonal form? What is a diagonal matrix? Well, basically a diagonal matrix is one where all of the elements, apart from those along the leading diagonal, are zero. So where I put these boxes, that's where you'd have non-zero elements, but everywhere else you would have zeros. So I'm going to have something like this, so maybe I'll highlight those in a specific color. So these ones in green, these can be non-zero, but all the other elements in that matrix must be zero. So when we reduce a matrix diagonal form, these elements here are going to be the only non-zero elements. Now that also means that the identity matrix is a diagonal matrix, because in the identity matrix, where I've got this blue highlight, these boxes here would be ones. Okay, so the identity matrix, or the identity I, is a diagonal matrix. Now you might be thinking, well, why do we need to do it? What's the point of changing or reducing the matrix to a diagonal matrix? Well, there are sort of two applications, one which we'll use and one which is really beyond further maths that you may use at university. So one use is to find powers of a matrix, and when it's reduced to diagonal form, that's easy to do. And also, if we want to solve vector differential equations, now that's beyond further two, but I'm sure you could probably find plenty of stuff about it online. But yeah, that's another reason we would use a diagonal matrix. Well, let's look at the method that we would use then to reduce a matrix to diagonal form. So we're going to start with a matrix that we'll call A. Okay, so this is our starting matrix, the matrix that we start with. I suppose I should put methods, because there are two ways, and the method you would use all depends on how easy it is to find the inverse of a matrix. So if the inverse of a matrix, not the matrix A, but if the inverse is easy to find, so for example in a 2 by 2, then we're going to use the method that I'm going to write on the left here. If finding the inverse is more difficult to do, so difficult, I suppose I should write inverse equals difficult to be consistent. So for example, in a 3 by 3, without a calculator, it's time consuming and fiddly to find the inverse of a 3 by 3 matrix, then we're going to use this method here. So we've got this starting matrix A. So let's start with the method on the left here, where we've got a matrix where the inverse is easy to find. Well, the first step is that we need to find the eigenvalues and eigenvectors, which we've done in a previous section. So you want to find the eigenvalues and the eigenvectors of our starting matrix A. So that's the first step. The second step is we're going to form a matrix that we will call P. Form a matrix P. Okay, that is made up of the eigenvectors, so what we've just worked out in the previous step, of the eigenvectors of A. So the first step, we would have calculated the eigenvalues so we can get the eigenvectors. Now the way that they are put into this matrix P is the first column is going to be the first eigen value, so I'll just put eig1, and the second column is going to be the second eigenvalue, like this. Okay, so I'm assuming we're talking about a 2 by 2 matrix. If it was 3 by 3, then it'd be the first eigen vector here, the second eigenvector here, and the third eigenvector there. So this matrix P is made up of these eigenvectors of A in columns. Now the third step, and this will decide whether you're going to use this method or the method on the right, is that we now need to find the inverse of P. So find the inverse of P. Now if P is a 2 by 2 matrix, that's going to be easy enough to do. But if it's a 3 by 3 matrix, this step is going to be time consuming, and then you'll use this method over here, which I'll show you in a moment. And then the last step, we can form our diagonal matrix, and our diagonal matrix, which we'll call D. So the diagonal matrix D is equal to P inverse times by the original matrix A times by P inverse. So this is the important bit here, is what we do with the matrix P, the eigenvector matrix, the inverse of P and A. So multiply them together and we'll get this diagonal matrix. And this matrix will be one where this leading diagonal will have values in, everything else will be 0. If that happens, you know you've done it right. Okay, so what if the inverse is not easy to find? What do we do? So the first thing we're going to need to do is we want to find the normalized. So remember, when you normalize something, you divide it by its length. So its length is 1. Find the normalized eigenvectors. So you'll have to find the eigenvalues first. So it's similar to this step here, but when we find this eigenvector, we're going to normalize it, but divide it by its length. So find the normalized eigenvectors of A. That's the first step. Then the second step is to write P equal to these normalized eigenvectors. So whereas in the first method, P was just made up of the eigenvectors, in this method, P is made up of the normalized eigenvectors. So just like before, we'll probably use this method for 3 by 3. We'll have a normalized eigenvector in this column, then the second normalized eigenvector in this column, and so on. So this is the method where we'd probably have 3 columns because we're using it on a 3 by 3. Now the reason why we'd use this method, because we don't need to find the inverse of P, we need to find something called PT, and PT is the transpose of P. Now this is something you would have done in Core 1 as part of the method of finding the inverse of a 3 by 3 matrix. You do the transpose of a matrix, and to find the transpose you just swap the rows and columns. Swap rows and columns. So basically what happens is the first row becomes the first column, the second row becomes the second column, and so on. Okay, so we found the normalized eigenvectors of A. Each one of those forms one column in this vector P, or matrix P. We find the transpose of that by reversing each row and column. So basically in PT we'll have the normalized eigenvectors going across each row like this, and then the diagonal matrix, D, D, well, this time it's equal to PT, so this transpose, times by A times by P. So you can see there's a slight difference. So one has the inverse of P, this one has the transpose of P. So I'll highlight this because this is the important bit about how we find this diagonal matrix. Okay, so let's just mention a couple of things. So let's go back to this bit here about finding the powers of a matrix and how this diagonal form is going to be useful. We're going to be looking at this way of finding the diagonal matrix. Okay, so D equals P transpose A P. Now it can be shown, and I'm not going to show it here, that A to the power K, so the matrix we start with, is equal to P times by D to the power K, P inverse. So if I want to calculate a matrix to a power, rather than multiply that matrix out many times, I can just apply this result here. So basically what we do, we find the diagonal form of the matrix A using one of these two methods over here, which is going to be D. We find matrix P and P inverse. And then all we need to do is to then multiply it out. Okay, now I just need to correct this. We didn't start with a transpose. We start with the inverse of P. So for example, let's say I wanted to find, I don't know, a matrix to the power 7. So that'll be my matrix P times by a diagonal matrix to the power 7 times by P inverse. Now, doing this matrix to the power 7 is going to be easy because we're going to have 0 here and 0 here. So basically, all you need to do is to take these elements and raise them to a power, like this. So if we go back to this, D to the power K is basically just going to be 0 here and 0 here. And it's going to be A to the power K here and D to the power K. So it's very easy to work out this diagonal matrix to a power because all we do is apply the power to these two elements, the first and last elements in this diagonal matrix. Now just a little note here that once we've worked out the matrix D, if we've done it correctly, then the elements or the non-zero elements of D will be the eigenvalues of A. So that's just like a little note there. So that will tell us whether we've worked out this diagonal matrix correctly or not. That these non-zero elements here will be the eigenvalues of the matrix A, the matrix that we're starting with. Okay, let's get into some examples. Okay, so in this question here, we've got this matrix A and we want to find a matrix P such that this is true where D is diagonal. So remember that the matrix P is made up of the eigen values of A. I think I'll spell that right. So in each column, eigenvalues. So if we want to find the eigenvalues, we need to start by finding the eigenvectors. We need to start by finding the eigenvalues. Right, so let's do that. Let's start by finding the eigenvalues of A. So to find the eigenvalues of A, we need to solve or form and solve this characteristic equation. So A minus lambda I equals 0. We'll take the shortcut and we'll just say that it's the determinant of, and then the first element minus lambda, and then the last element minus lambda. I'll just tidy up, that's 3 and 2. And that's going to equal 0. So we can now multiply it out or find a determinant. So AD, so 4 minus lambda, times by 2 minus lambda. Sorry, that should be 3, shouldn't it? I rubbed them out and then wrote them down wrong. So yeah, it should be 3 minus lambda minus a times d, so minus 2 times 1, or sorry, b times c equals 0. Multiplying that out, I'll get 12 minus 4 lambda minus 3 lambda plus lambda squared minus 2 equals 0. So that will give me lambda squared minus 7 lambda, 12 minus 2 plus 10 equals 0. So I'm thinking 5 and 2 will factorize that. And minus 5 and minus 2. So then I have my eigenvalues of 5 and 2. Right, let's start with the eigenvalue of 2 and use that to work out what the eigenvector is. So that's going to be 4, 2, 1, 3 times by this vector xy that's going to get scaled to 2 times xy. So let's write out our equations. So we'll have top row 4x plus 2y equals 2x. Bottom row will give us x plus 3y equals 2y. So the top equation will give us 2x equals minus 2y. Now what does the bottom one give us? X equals minus y. So they're both telling us the same relationship, that x equals negative y. So if, for example, I let x equal to 1, that will give me an eigenvector of 1 minus 1. Okay, let's just highlight that because that's going to be my first eigenvector. Highlight it rather than draw over it. And we'll now go on to lambda equals 5 and calculate the other eigenvector. So the scaling now is going to be 5 rather than 2. We'll write our equations. So we'll have 4x plus 2y. So the only thing that's going to change actually is the right hand side. So we could just copy down what the left hand side is going to be. That's going to be the same. It's just the 2's and we'll now change to 5's. Let's see what relationship that gives us. So that will give us x equals 2y from the top one, if I take away 4x from both sides here. And then the bottom one, that will also give us x equals 2y. Okay, so there's our relationship, x equals 2y. So let's make y equal to 1, so I don't end up with halves. And that will give me this eigenvector, 1 for y, and that means that x is 2. So 2, 1 is my second eigenvector. So my matrix P is made up of these eigenvectors. Now, I could have any multiples of these vectors here, and actually I've worked out this one first and this one second, so I'm going to put this in the first column and the second column, but it doesn't matter. If you have it switched the other way around, it still works. Yeah, there's nothing that says that a certain eigenvector, eigenvalue or eigenvector needs to go in a particular column. So I'm only going to put this in the first column because I worked that out first. So I've got 1 minus 1, 2, 1, or you could have 2, 1 here and 1 minus 1 here. Okay, so here's my P matrix, and in part B is we want to find this diagonal matrix D. Okay, how are we going to find that? By doing P inverse times by A, this matrix times by P, which we've got. So now we want to find P inverse. Now we could use our calculator to do this, but actually probably by the time you've gone into the right menu, typed in the values, pressed the x to the -1 button and done all of that, you probably could have worked it out manually. So first of all, we want 1 over the determinant. So the determinant is going to be AD minus BC. So it's basically going to be 1 plus or minus 2. So it's going to be 3. And then remember, we swap the elements A and D, and we reverse the signs of B and C. So if we swap A and D, they're still going to be 1s. Reverse the signs of B and C, and we're done. And if you were doing this on a calculator, you're probably still typing it in. So there's my inverse. So now we're going to multiply these together. So D is equal to P inverse, which we just worked out, 1/3, 1, negative 2, 1, 1, times by A, which is 4, 2, 1, 3, and then times by P, which is 1, 2, negative 1, 1. So we need to multiply pairs of them. We can only do 2 at a time, or you could type all of this in a calculator, but again, I think by the time you've typed all of this in, it's going to take quite a while. You probably could have done it manually. So let's start by multiplying those two matrices out. So we're going to have 1/3, and so we're doing now this one times by this one here. Right, so when we multiply those first two matrices together, we're going to get the matrix 2, negative 4, 5, 5. We multiply that by the 1, 2, negative 1, 1. So that will give us D is equal to 1/3 of, now when we multiply these two matrices together, we'll get 2 plus 4, which is 6. Then we'll have 4 minus 4, which is 0. Then we'll have 5 minus 5, which is 0. And then we'll have 10 plus 5, which is 15. And if we find 1/3 of those elements, we'll just have our diagonal matrix as 2, 1/3 of 6 is 2, and 1/3 of 15 is 5. Now, how do we know that's right? Well, there's a couple of things. Is it a diagonal matrix? Yes, because along this leading diagonal, I have non-zero elements and everything else is 0, so it's the right form. And what else do we know? Well, these two numbers should be the eigenvalues of the original matrix A, and if we go back, the eigenvalues were 2 and 5. So we know that this is correct. Okay, so this question says that we want to reduce A to a diagonal matrix. Now it doesn't say which method we need to use, so we could either use the one where we find the inverse of P, or we could use the method where we find the transpose of P. Now finding a transpose is easier than finding the inverse, probably even with a 2 by 2. So we're going to use that method. So we're going to use the method where once we found P, we find the transpose of P. We could just as easily do it by finding inverse, and we'll get the same result. So the first thing that we need to do is we want to find the eigenvalues. So that means forming and solving this equation. So we'll just state that. So that's the determinant of 2 minus lambda, negative 1, 2 minus lambda equals 0. Let's find a determinant. So that's going to be A times by D minus negative 1 times by negative 1 equals 0. We'll multiply that out and we will get 4 minus 2 lambda plus lambda squared, and minus 1 equals 0. So we'll get this equation, lambda squared minus 4 lambda plus 3 equals 0. Right, so this is going to factorize with a negative 3 and a negative 1. So that gives me my eigenvalues of 1 and 3. So we now need to find our eigenvectors. So they are going to scale our matrix by 1 and 3. So we'll start with the one that scales a vector by 1. So maybe I should put somewhere that, or maybe highlight here, that I'm dealing with the eigenvector of 1 first. So that's going to give me these equations. 2x minus y equals x, and negative x plus 2y equals y. So what equations does that give us? So taking away x from both sides, so we'll get x equals y from the first one. Do we get x equals y from the second one? Let's have a look. Well, we get negative x equals negative y. So it's telling us the same piece of information, that x equals y. So if we let x equals 1, let's go for the simplest eigenvector, which is just going to be 1, 1. Okay, let's color code it. So all of this is for our eigen value of 1. So now let's go for our eigenvalue of 3 and see what that gives us. So when we write our equations down, the only thing that's going to change is the coefficient of x and y on the right hand side of the equation. So 2x minus y is 3y, 3x, negative x plus 2y equals 3y. So what do we get from here? So I'll get x equals y. Sorry, x equals negative y. And for the bottom one, if we take away 2y from both sides, we'll have negative x equals y. So it's given us the same piece of information, that x equals negative y. So let's make x equal to 1. So that will give us the eigenvector 1, negative 1. So let's highlight that in green, because this all relates to the eigen value of 3. Now, because I'm using the transpose method as opposed to the inverse method, that does mean I need to normalize my eigen vectors. So that means dividing them by their length. Now I can see for the first matrix here, its length is going to be the square root of 1 squared plus 1 squared. So it's got a length of root 2. So I need to divide both of those elements by root 2. And the same here, this has a length of root 2, the size of this vector, the modulus of this vector. Square root of 1 squared plus negative 1 all squared will also give me root 2. So my normalized eigenvectors now become 1 over root 2, 1 over root 2. Then the second eigenvector becomes 1 over root 2, negative 1 over root 2. So that's the only extra step that's required that you wouldn't need for the inverse method. We just form a vector p of the eigenvectors, sorry, not the normalized eigenvalues vectors. Right, so my vector p is going to be made up. Its columns are going to be these normalized eigenvectors. So 1 over root 2, 1 over root 2, and the second column 1 over root 2, negative 1 over root 2. The next step now is to find the transpose of p. So we just swap the rows and columns. So basically the first row here is going to become the first column here, and the second row, what color can we use? Let's use yellow again. The second row becomes the second column. So our first column is going to be 1 over root 2, 1 over root 2. The second column is going to be 1 over root 2, negative 1 over root 2. So you can see it actually doesn't look any different, even though we've swapped these rows with the columns. Now you could think of it the other way, that that first row becomes the first column. This second row becomes, sorry, this second column becomes the second row. So whichever way you do it, that's P transpose. So now D, the diagonal matrix we're trying to find, is equal to P transpose times by A times by P. So now we're going to work that out. So that's going to be P transpose. So this matrix with the negative 1 over root 2 here times by matrix A, which is 2, negative 1, negative 1, 2, times by P, which is exactly the same as P transpose in this example. And then we'll multiply these out. Okay, now because of all the multiplying by 1 over root 2, I actually did this on the calculator. And actually you can save a bit of time because I define this matrix here on the calculator as matrix A. I define this matrix here, so that's meant to be DEF for defined. This one as matrix B, and because the third matrix is the same as the first one, I didn't define this as anything. So when I did the calculation on my calculator, I just did matrix A times by matrix B times by matrix A. So I only had to type in this matrix once because it gets repeated here. And then doing that on my calculator, I got this diagonal matrix as 1, 0, 0, 3. So that was probably quicker than actually multiplying it out manually. And we'll check it's in the right form because I've got these elements 1 and 3 on the leading diagonals, and 1 and 3 should be the eigen values, and they are. Now we could also have used the other method where we find the inverse of the matrix P rather than normalize it. So we'd have P as 1, 1, 1, negative 1. So we'd have that in the first column, that in the second column. Find the inverse of that and use that method. We would have got the same answer. Okay, so in this question we've got this matrix A and we want to find a matrix P and a diagonal matrix D such that D equals P inverse AP. Now when we come to this bit, P inverse, when we define a matrix, we're going to use our calculator for this. When we define a matrix A, for example, that's going to be what I type in for matrix P, which we'll work out in a moment. That's P is going to be the matrix of the eigenvectors of A. So we're going to have to start by finding the eigenvalues, then the eigenvectors. Then when we want P inverse, then all we do is we're going to press the button that brings up matrix A, and then we're going to press the x to the -1 button, and that would be P inverse. So that will save us time. So we are allowed to use our calculator. It will save us time. So the eigenvalues are going to be found when we solve this characteristic equation. So that will be the determinant of this matrix. So 1 minus lambda, 1, 2, 4, 2 minus lambda, negative 3, 4, 2, 3 minus lambda, all equal to 0. So let's write down what that's going to be. Well, it's going to be 1 minus lambda times by its minor, which is 2 minus lambda, or the determinant of this, 2 minus lambda minus 3 to 3 minus lambda. Then minus 1 times by its minor, which is going to be the determinant of 4, negative 3, 4, 3 minus lambda. And then plus 2 times by its minor, which is going to be the determinant of 4, 2 minus lambda, FP2 equal to 0. So we've got a lot of multiplying out to do. So I'll pause it and write down what we get once we've worked out the determinants. So this is what we get here once we've worked out the minors. Now what we'll do, we'll expand this and simplify it. So again, I'll pause it and write down what this becomes once this is all expanded, and then we'll simplify it afterwards. Okay, so this is what we get when those brackets are expanded out. I'm not going to go through all the working, you should be able to do that. And then when this first bracket is expanded, and when all of this is simplified, we end up with this cubic, negative lambda cubed plus 6 lambda squared minus 5 lambda minus 12 equals 0. Now, we've not been given any of the eigenvalues, so it's not as if we could say, right, we know what one of the roots is, let's put that in a bracket and then use equating coefficients or long division to work out what the quadratic is. So we're going to use our calculator to work out what the roots are. So remember, if we're going to do this and we're going to use our calculator to solve it, we want, and I'll write the instructions down here, we want menu, and the solve menu is number A. So A, and then from that we want a polynomial, so it's 2, and the degree of that polynomial is 3, so we just do 2 and then we do 3, and then we'll just put the coefficients in. So we'll just put -1, 6, and after each one we will press the equals button, -5 and 12, -12. So we're doing this because, as I said, unless we guess what the roots are, we're not going to find out what they are. So if we do that, the values we get are lambda equals -1, lambda equals 3, so these are the roots, and lambda equals 4. Right, so let's start with the eigenvalue of -1. So 1, 1, 2, 4, 2, -3, 4, 2, 3. And since we're doing 3 of them, I'm not going to write all of the working out 3 times. I'm just going to basically use what I've written here and just change the eigenvalue and then write the new sets of equations. Right, so with an eigenvalue of -1, we're going to get the following 3 equations. So x plus y plus 2z equals -x, 4x plus 2y minus 3z equals -y, and 4x plus 2y plus 3z equals -z. So if we rearrange them to make them equal to 0, so adding x to both sides, we'll have 2x plus y plus 2z equals 0. Second equation, add y to both sides, we'll have 4x plus 3y minus 3z equals 0. And then the bottom equation, add z to both sides, we'll have 4x plus 2y plus 4z equals 0. Okay, now the first and last equations actually tell us exactly the same thing. They're equivalent. If you times all of those by 2, you get this. But because these last 2 equations here have the same coefficient of x, it's useful then to subtract one equation from the other. So if we do that, we'll have y minus 7z equals 0. So that gives us the relationship between y and z. So y equals 7z. So that gives us a relationship between y and z. Now if we substitute y for 7z here, this will give us 2x plus 7z plus 2z, so 2x plus 9z equals 0, or in other words, x equals -9z. So if I then made z equal to 1, I would have y equal to 7, and dividing both sides of this by 2, so that x equals negative 9 over 2z, that would mean that x would equal negative 9 over 2. So there's my first eigenvector. Now let's just multiply it by 2 so that we're dealing with whole numbers. So I'll have negative 9, 14, 2. So what I'm going to do down here is write down the matrix P. So my first row is going to be that negative 9, 14, 2. Right, so all I'm going to do now is replace this number with the next eigenvalue, which is 3. Then that means that these numbers here will just become 3. So rather than write the whole thing out again, it'll just take up loads of space. Obviously now that's going to change our equations that we got over here, so I'll just clear this, and then what we'll do is we'll write down what those new equations are. Okay, so I've written down here what the 3 equations we're going to get when the eigenvalue is 3. And here I've simplified them. Now the bottom one just has x and y in, so that's going to give us the relationship between x and y. So if you divide both sides by 2, then we'll get 2x equals negative y, or y equals, or negative 2x equals y. So I will make x equal to 1. Okay, and then that will mean that y equals negative 2. So all I need to do now is to work out what z is going to equal. And then I can substitute this relationship, let's say, into the second equation here, and replace that negative y with 2x. So I'll have 4x plus 2x, which is 6x. So I'll end up with this 6x minus 3z equals 0. In other words, 6x equals 3z. So that's the same as 2x equals z. So I've made x equal to 1, which means that z is going to equal 2. So there we go. Here's our second eigenvector. So I'll put 1, negative 2, 2. So I'm now ready to do the last one, which means just replacing those 3's there with 4. So that's my last eigenvalue. So 4, and we'll put 4's here. We'll rub this out, and then we'll work out what those new equations are. Okay, so these are the sets of equations that we get here. Now notice I've got the same coefficients here, so I could subtract these equations to get rid of x to find the relationship between y and z. That will give me negative 4y minus 2z equals 0. So it's telling me the relationship between x and y. If I divide both by 2, I'll get negative 2y equals z. So I will make y equal to 1, which means z is going to equal negative 2. So I've got 2 of my values. And then what I can do, I could use this, or basically I've got negative 4y equals 2z, and replace that 2z with negative 4y. Now if I do that, replace the z with negative, or the 2z with negative 4y. So that would give me negative 3x, and then the negative 4y plus y would give me negative 3y equals 0. The relationship between x and y then is going to be negative 3x equals 3y. Divide both by 3, and I'll get negative x equals y. So there's my relationship. Since I've made y equals to 1 using this, it means that x is negative 1. So this now is the last column of P. So negative 1, 1, 2. So that's sort of the first part, isn't it? We found what P is. Now we know what D is going to be. D is going to be the matrix, the diagonal matrix where the leading diagonals are the eigenvalues in the same order as I've done them here. So this was the eigenvector for -1. This column was the eigenvector for the eigenvalue of 3. And the last column was the eigenvector for the eigenvalue of 4. Now we want to check this on our calculator. So we're going to go into matrix mode on our calculator. We'll enter this matrix here for A, and we'll enter this matrix here, and then we'll use the inverse button to do the inverse of this times by A times by this, and check that we get the same answer. Okay, I did check out my calculator. It does work once I realized that I'd actually missed the -1 there, and it does give me the matrix D. But you just need to make sure that the eigenvectors match up with your eigenvalues. So if, you know, I had these eigenvectors in a different order, so if I had a -9, 14, 2 in the last column, I would need to make sure that I've got -1 in the last column. So do make sure that they match. So here's our matrix P, which was the vast majority of the working, and the matrix D, which we can just basically form straight away because we know that the leading diagonals are going to be the eigenvalues in the same order as the eigenvectors. Okay, so we've got this matrix A here, and we want to verify that this is an eigenvector of A, and we want to find the corresponding eigenvalue. Well, if it's an eigenvector, that means that if we multiply that vector by A, the matrix, which I'm just writing out now, then we should get a multiple of that matrix, a scaling of that matrix, or scaling of this vector, and we want to work out what that scaling is. Okay, so let's work out what we get when this all gets multiplied. So 7 times by 2 is 14, plus 5, that's going to be 24. Then if I go to the second row here, and this column, so 5 times 2 is 10, 10 minus 2 is 8, 8 plus 4 is 12, this is going to be 12. Then the bottom row, 5 times 2 is 10, 10 plus 4 is 14, minus 2 is 12. So I can see that yes, the vector is a scaling, and it's a scaling of 12, and it's 12 times bigger than the original one. So for part A, I can say that since that matrix times by 2, 1, 1 equals 12 lots of 2, 1, 1, the vector is an eigenvector, and its eigenvalue is 12, because that was the scaling. Okay, part B. Show that -6 is another eigenvalue of A and the corresponding eigenvector. Okay, so it's like part A, but it's just like the other way around now, where it's the eigenvector we don't know, the eigenvalue we know. So we just write down the same thing, but this time the unknown will be this vector, which we'll call x, y, z. But what we do know is that it's a scaling of -6. So this is where we just write our equations and solve them. So we'll have 3 sets of equations. We'll have 7x plus 5y plus 5z equals -6x. Second row, 5x minus 2y plus 4z equals -6y, and then 5x plus 4y minus 2z equals -6z. So what I've done here, I've put down what these equations become once we've added 6x, 6y and 6z to both sides. We end up with these. Now you can see that the last two equations end up being the same, so we can cross the last one out because we're not going to get anything extra from that. So we can only use these two. So we need some way of solving them simultaneously. Now what I notice is that the coefficients between the x and y's are the same. So what I can do with the top line, if I divide everything by 5, I'll get 13 over 5x plus y plus z equals 0. And then from the one underneath, divide everything by 4, I'll get 5 over 4x plus y plus z equals 0. Now what I can do is subtract one from the other. So I'll get 13 over 5 minus 5 over 4, which will leave me with 27 over 20x, 27 over 20. And then, like, if I subtract these, they're all gone. So what do I get? I end up with basically that equal to 0, which then follows then that x equals 0. Okay, so there's my first solution. Then what happens is that the remaining parts of the equations here, if x is equal to 0, I basically end up with the equation y equals negative x from both of these. So then I could say make z equal to 1, and then y would be negative 1, or vice versa. So I'll just put down here that we'll have z equal, make that equal to 1, so y equals negative 1. So that will give us this vector 0, eigenvector negative 1, 1. So that is the vector that corresponds to the eigenvalue of negative 6. So we'll just highlight that before we move on to part C. And part C says, given that the third eigenvector of A is this, find a matrix P and a diagonal matrix D such that P transpose AP equals D. Right, so we now have the 3 columns that we need for the matrix P before we normalize it. So in the first column, I'm going to put the eigenvector for part A. What was that? 12. So I'm just going to write this up here. So for the eigenvector of 12, I got this matrix that was in part A. For the eigenvector negative 6, for the eigenvalue negative 6, we got the eigenvector of 0, negative 1, 1. Now in the last part of the question, we don't know what the eigenvalue is, but we do know what the eigenvector is. That's going to be 1, negative 1, negative 1. Now we're going to have to find what that eigenvalue is by doing the same type of method that we did in part A, because we want to use that to check D, because D is going to have the eigenvalues of 12, negative 6, and this one here. So we'll do that in a minute. So my unnormalized matrix for P is going to be, I'm going to put the eigenvector for 12 first. So this is what I'm expecting for D. So D should be 12, 0, 0, then 0, negative 6, 0. So I'm going to put this vector in the second column, 0, negative 1, 1. But as yet, I don't know what eigenvalue to put here. So it's going to be 0, 0. We'll work that out in a moment. So we'll find out what needs to go here in a moment. But yeah, in the last column of this unnormalized matrix is going to be 1, negative 1, negative 1. So let's normalize it, which means we need to divide each of the eigenvectors by their lengths. So in the first column here, dividing that vector by its length, so it's going to be 2 squared plus 1 squared plus 1 squared. So that's 4 plus 1 plus 1. which is 6. So the length of this vector is root 6. So I'm going to divide those by root 6. The second one, 0 squared plus negative 1 squared plus 1 squared. Well, that's going to be 2. So square root of 2 is the length of that vector, which I'm going to divide it by. The last column, this will be root 3 because it's going to be 1 squared plus negative 1 squared plus negative 1 squared. So this is going to be divided by root 3. So my normalized matrix for P is going to be 2 over root 6, 1 over root 6, 1 over root 6. Second column, 0, negative 1 over root 2, and 1 over root 2. And then the last column will be 1 over root 3, negative 1 over root 3, and negative 1 over root 3 again. So that's my matrix P. Then I'm going to do P transpose, which is swapping the rows and columns. So this top row is going to go in the first column. So that will be 2 over root 6, 0, 1 over root 3. Second row is going to go in the second column, so that's 1 over root 6, negative 1 over root 2, 1 over, or negative 1 over root 3. And then the bottom row here is going to go in the last column. So that's going to be 1 over root 6, 1 over root 2, and negative 1 over root 3. Now when you do this, it's always worth double checking that you've done that correctly. So that should be here, which it is. This should be here, which it is, and this bottom row should be here, over here, as it is. Now, as I said, you can do it the other way. You can say, right, this first column should be in this first row. This second column should be in the second row. This third column should be in the third row. As long as we swap the rows and columns, we get the transpose. Now I'm going to make a bit of space for the rest of part C because we need to work out the eigenvalue that goes with that eigenvector that's been given in part C. Okay, let's find this eigenvalue then. So 7, 5, 5, 5, minus 2, 4, 5, 4, minus 2. We want to find out what it scales this vector by, so we just need to multiply it out. So we've got 7 minus 5, which is 2, minus another 5, which gives us negative 3. The second row, so we've got 5 plus 2, which is 7. 7 minus 4 is going to be 3. And then the bottom row, 5 minus 4, which is 1, and then 1 plus 2 is going to be 3. So I can see that the scaling here is times by negative 3. So that is the eigenvalue that goes with this vector. So now I don't need to multiply P transpose AP. I know that D is going to be equal to the eigenvectors or the eigenvalues. So my first eigenvalue was 12. The second one was negative 6. And that last one that I've worked out is negative 3. And that matches up with the matrix that I've done for P, because that's the same order. Eigenvector for 12, eigenvector for negative 6, eigenvector for negative 3. If you swap the order of these vectors, make sure that these eigenvalues match up with them. These need to be swapped as well. Okay, so in this example here, what we've got is an application of vectors or matrices, eigenvalues and eigenvectors. What we've got here is two recurrence relations. Okay, one in terms of x, one in terms of y, and both of those recurrence relations can be expressed in this form. So basically it's saying if you multiply this vector here, or basically the current terms, by this matrix, you'll get the next set of terms. Here we have the initial conditions. This vector represents the initial conditions. And you can see here 4, 1, 2, 3, they're the coefficients of these values here. So basically all we've done is we've put this into matrix form and we represent this recurrence relation with a matrix. So we'll start with part A, and it says find the eigenvalues and corresponding eigenvectors of A. Right, so what we will do, we know that to find A, it's the determinant of A minus lambda I equals 0. So that will be the determinant of, and I suppose I could put it in like these lines here to show that I'm finding the determinant. I normally write the determinant of it. Let's do it this way for a change. So minus lambda along the leading diagonals equals 0. Okay, so let's work out what that determinant is. So it's going to be 4 minus lambda times by 3 minus lambda minus 1 times 2 equals 0. So from there, if we multiply out the brackets, we'll get 12 minus 3 lambda minus 4 lambda, which is minus 7 lambda, plus lambda squared, plus, minus 2 equals 0. Minus 2 equals 0. And that gives us this quadratic, lambda squared minus 7 lambda plus 10, 12 minus 2 equals 0. That does factorize. And our values are going to be 5 and 2, because we want to make minus 7 and plus 10. So that gives us our eigenvalues of 5 and 2. So we'll just write down here eigenvalues are 5 and 2. Okay, I'll just highlight that, and then we need to find the corresponding eigenvectors. Right, so 5 and 2 are the two scalings that this matrix produces. So let's find those. Let's start with lambda equals 5 and work out what the eigenvectors are. So 4, 1, 2, 3 times by the vector we want to find, xy, is scaled by 5. So the equations this gives us are 4x plus y equals 5x and 2x plus 3y equals 5y. Now let's see what equation or equations this gives us. So the top one, that will reduce to x equals y if we take 4x away from both sides, and the bottom one will reduce to 2x equals 2y if we take away 3y from both sides. They're both telling us the same thing, that x equals y. So if we say let x equal 1, that gives us an eigenvector of 1, 1. Let's do the same now for lambda equals 2 and find its eigenvector. So that's going to be 4, 1, 2, 3 times by xy, and the scaling this time is 2, so the vector xy gets scaled by 2. So the equations that's going to give us are 4x plus y equals 2x and 2x plus 3y equals 2y. So the only thing that changes from these sets of equations to these is this scaling here, 5 here and 2 here. So if you wanted to speed things up a bit, you could basically just copy this out and change this value 5 to 2, change it to the other eigen value. Right, so what happens here? Well, the top equation here, if we take 2x away from both sides and move the y across, we'll get 2x equals negative y. Now let's have a look at the bottom. Let's see what happens with that. If we take 3y away from both sides, again we get the same equation, the same relationship, 2x equals negative y. So we'll say let x equals 1, make it nice and easy. So that gives us an eigenvector of 1, negative 2. So I'll just highlight that. Here are the corresponding eigenvectors. So for 5, we get 1, 1, and for eigenvalue of 2, we get 1, negative 2. So that will be our part A done. Now part B, what we need to do is to hence write down matrices P and D such that P inverse AP equals D, where D is a diagonal matrix. So remember, P is going to be the matrix where its columns are the eigenvectors. So if I use the 1 for lambda equals 5 first, so that'd be 1, 1. And then the eigenvector for lambda equals 2, or eigenvalue 2, 1, negative 2. Now for D, remember the elements of D along that leading diagonal are just going to be the associated eigenvalues. They need to be in the same order. So since this is the eigenvector for 5, then this needs to be 5. And since this second column is the eigenvector for 2, R2 needs to be here. So that's a nice easy part of the question, because we're just basically just copying down the things we'd worked out from part A. Okay, now there's some new information here. Let's have a look and see what it says. So it says new sequences UN and VN can be formed from XN and YN using this transformation. Okay, let's just put a little thing around that transformation. Show that this statement here is true. Right, so since we've just been given this piece of information here, this is what we're going to start with. So we'll start by writing UNVN equals P inverse XN YN. So that's the first step. Now you'll notice that what we want to get to has got UN plus 1, VN plus 1. So what we're going to do is just replace N with N plus 1. So if we do that, then the next step, what we'll have is this UN plus 1, VN plus 1 equals, and let me just move this out of the way. We might need these later. So what I'll do, I'll just write them elsewhere for now. So here they are, they're highlighted here in case we need them. I'm sure we probably will need them. Yep, so what we were doing, we were replacing N with N plus 1. So now we'll have P inverse, and then here we'll have XN plus 1, and then YN plus 1. So that's our step number 1. So look at what we want to get to, and let's think about what we're going to do next. So we've got this side matched up. Now we've got another relationship that we've been told up here. Now let's have a look at what we've got. We've got XN plus 1, YN plus 1, and we've got that here, and it's equal to this. So what that means is I can substitute this here for A, X, N, Y, N. So let's do that. So that'll be the next step. So I'll have UN plus 1, VN plus 1 is equal to P inverse, and then A, so this is a substitution, XN, YN. Okay, let's think about what we want to do next. Well, I actually want to end up with D here, and I know D is equal to P inverse AP, and I've got the P inverse A. Now, what if I multiplied by P inverse here, which is basically the identity? So if I multiplied by P in E inverse, which is the identity, this doesn't change. It's what it actually means. So that's what I'm going to do, and then maybe there's something I can do with the P inverse and this bit here. So let's write that down. So the next step, we'll have UN plus 1, VN plus 1 equals, then we've got P inverse A, and then P inverse, so that's the identity, so doesn't change it, and then XN, YN. Now I've done that, and I noticed that this here is this, isn't it? So this can be substituted for un vn. So we'll do that next. So un plus 1, vn plus 1. Then we've still got the p inverse, or equals p inverse a p, but then the p inverse xn yn can be changed to un vn. Now we know what this equals. This equals D, the diagonal matrix. So what we can do for the next step is to replace P inverse AP with D, and we'll end up with UN plus 1 VN plus 1 equals D UN VN, and we've proved it as required. We've now got to this format here, so we can just put as required, or we can put QED. We've proved what they've wanted. Okay, we're going to move on to part D now. Now I've got a fresh slide here because we're going to need plenty of space for this. I've highlighted all of the different relationships we've been given and written down the values of P and D. Now it says D, hence find a closed form or solution for the expressions of the original sequences x, n and yn. Now what have we got? We've got something for the I suppose what we can call the transformed recurrence relation. So these values here, v and u, and we want to change it or transform it back so that we've got x and y. So let's start with the relationship that we've been given. So un plus 1 vn plus 1 is equal to d times by un vn, and then we know what d is, so we can replace d with 5002, so we'll do that. So now we've got 5002 times by un vn. So what we'll do is we'll multiply that out, and it will give us these recurrence relations in terms of u and v. So we'll get un plus 1 equals 5un, and we'll also get vn plus 1 equals 2vn. Now these are first order homogeneous recurrence relations, and we've looked at how we solve these in the previous chapter. And just as a reminder, if we've got a recurrence relation in this form, un equals a times by u to the n, or un minus 1, then the solution to that is either going to be un equals u0 times by a to the power n, or un equals u1 times by a to the power n minus 1. Now it all depends on whether we have been given u0 or u1. Now if we have a look back here, we've been given x1, y1, so we're going to use the second form down here. So this is going to be our general solution here, because of our initial values are not x0 and y0, but x1 and y1. Now you'll notice that these are un plus 1 and vn plus 1, and here we've got un. Now these can be written in an equivalent form, and actually these are the same as, so if we basically just take one away from n, so the two equations become or the recurrence relations become un equals 5 un minus 1. So it's still the same relationship, the previous term and the next term, so n plus 1, so basically just adding 1 to n, and then the bottom one will become vn equals 2 vn minus 1. So these are equivalent to these. So now it's in this sort of format, and then we can now apply this to find a general solution. So the general solutions will be un equals u1 times by a is 5 in the first one, 5 to the power n minus 1, and then vn equals v1 times by 2 to the power n minus 1. So I'll just write down here that what we've got here are the general solutions. So what we've got here are the general solutions in terms of u and v. We want general solutions in terms of x and y. That's where we can use this. This is the transformation that is going to change from uv to xy. But at the moment, what this is saying is, right, you start with xy, you multiply it by p inverse, and you get uv. We want to rearrange this to say, right, we start with uv, we apply some sort of matrix transformation, and we get xy. So we can say something like, since un vn equals p inverse x and yn, by left multiplying by p, in other words, multiply by p on this side here and p on this side here, what we're going to end up with is now this relationship, p times by un vn equals, now we're left multiplying by p, so we'll have p times p inverse, which is the identity, so we're just left with xn yn. So what we've got now, this tells us how to change the recurrence relation, the solution to recurrence relation in terms of u and v, how to change it to x and y. Okay, so what we'll do is we'll just spin it around. So we'll have xn yn equals p. Now p is that 1, 1, 1, negative 2 matrix times by uv, or un vn. We'll multiply that out. This will give us the relationship. Xn is equal to un plus vn, and yn is equal to un minus 2vn. Right, now we can replace un and vn with the general solutions here. So what we'll have next is xn is equal to un, and un is u1 times by 5 to the power n minus 1, plus vn, and vn is v1 times by 2 to the power n minus 1, and yn is equal to un again, so that's u1 times by 5 to the power n minus 1, minus 2 times vn, and that is v1 times by 2 to the power n minus 1. Now we can use the initial conditions to work out the values of u1 and v1, and then we're finished. Now the initial conditions will be n equals 1, and when n equals 1, we've got the initial conditions up here. X1 is 1 and y1 is 2. So we just substitute that in. So with the top equation here, n is going to be 1, so x1, which is 1, equals, now since n is 1, we're going to end up with 5 to the power 0 here, 1 minus 1, and 2 to the power 0. So effectively all we'll end up with is u1 plus v1, because these are just going to become 1 because n is 1. They're going to become 1 because the power is 0. So we end up with 1 equals u1 plus v1. If we do the same with the bottom, so here we're going to have y1, so that's 2. And then just like the top equations, when n equals 1, this will become 5 to the power 0. This is 2 to the power 0. So all we'll be left with is u1 minus 2v1. So u1 minus 2v1. Right, and then we can use the simultaneous equations to work out what the value of u1 and v1 are. So let's subtract these and see what we get. So we'll have minus 1 here, the u1s will cancel out, and then we'll have v1 plus 2v1, so we'll have 3v1. So that gives us v1 is equal to negative a third. Now we can easily substitute that into this equation here. So if we've got 1 here and we've got negative a third, what minus a third is 1? Well, 4 over 3. So it follows then that u1 is equal to 4 over 3. Right, we've now got these values here. They can go into our equations and we're finished. So xn is equal to u1, which is 4 thirds, times by 5 to the power n minus 1, plus v1 times 2 to the power n minus 1. Now v1 is negative a third, so we can just write down minus a third times by 2 to the power n minus 1. So that's the first recurrence relation, the closed form, the solution, and then yn is equal to u1, which is 4 thirds. So we've got 4 thirds times by 5 to the power n minus 1, minus 2 times v1. So if we're minusing 2 times minus a third, we're going to be adding 2 thirds. So plus 2 thirds times by 2 to the power n minus 1. So then this becomes our final solution. This is the closed form of the original sequence. Now you can see there's lots of little bits and pieces to answer this question. So this is going to be one of those questions where it's may not be worth lots and lots of marks, but it's definitely a bit more challenging than some of the more straightforward questions that we've been doing. Okay, so here we've got matrix A, and the question says find a matrix P and a diagonal matrix D such that P inverse AP equals D. Okay, so this should be nice and straightforward for us. So we want to find a determinant of this matrix here, and solve this characteristic equation. So it's going to be the determinant of 3 minus lambda, 1, 2, 2 minus lambda equals 0. So that's going to give us this 3 minus lambda, 2 minus lambda times 2 minus lambda, minus 1 times 2 equals 0. So that will give us 6 minus 2 lambda minus 3 lambda, so minus 5 lambda plus lambda squared minus 2 equals 0, and that gives us lambda squared minus 5 lambda plus 4 equals 0. So this will factorize. It's going to be 4 and 1 in the brackets, and we want minus 5, so it'll be minus 4 minus 1. So our values of lambda, our eigenvalues are 4 and 1. So we'll just write down eigenvalues are 4 and 1. Okay, so these are the values that are going to go into our matrix D. So that'll be 4, 0, 0, 1. But let's find the eigenvectors to find out what goes into P. So let's start with lambda equals 4, or eigenvalue equals 4. So that will be 3, 1, 2, 2 xy, and the scaling is 4 this time. So the equations we're going to get are 3x plus y equals 4x, and we'll have 2x plus 2y equals 4y. Let's see what equations that gives us. So for the top one, if we let's say take away 3x from both sides, we'll end up with x equals y. We'll do the same for the bottom. We should get the same equation. So if we take away 2y from both sides, then we'll get 2x equals 2y, so that's telling us the same information. We'll let x equals 1, and that will give us an eigenvector of 1, 1. So now we'll go for our eigenvalue of 1. So not much is going to change, really. All of this is the same. This first part is the same, apart from our scaling is 1 this time. And the equations we're going to have are 3x plus y equals x, and 2x plus 2y equals y. We'll see what we get with these ones. Take away x from both sides, so I'll end up with 2x equals minus y. And then for the bottom one, take away 2y from both sides, again end up with the same information. So if I let x equals 1, I'll end up with the eigenvector of 1 minus 2. Okay, so now I'm ready to write down what D and P are. So P will be 1, 1, my first eigenvector, 1, negative 2. And my diagonal matrix D is going to be my first eigenvalue, so that was 4. And then my second eigenvalue, which was 1 here. Okay, now part B asks us to work out a to the power 6. Now we're going to use this relationship here, that if we want to find the power of a matrix, let's say matrix to the power k, that's equal to P times the diagonal matrix to the power k times by P inverse. So this is what we're going to use. So the only other thing that we need to find is the inverse of P, and we can use our calculator to find that. So P inverse. So I'm just going to do that now. So we'll do menu, then option 4, we'll go in, we'll type the matrix values in. Now, if you're using a class-wiz calculator, you'll notice that you'll get decimals, but as you hover over each of those values, you'll get the exact value in the corner, and you'll see you'll get 2/3, 1/3, 1/3, minus a third. So it may be that we decide to take the 1/3 out, or we could leave it like this. So 2/3, just about squeeze this in here, 1/3, then the bottom row is going to be 1/3 here, and minus a third. So you could, if you wanted to, actually factorize out the third. So now to find a to the power 6, we're going to do P times by D to the power 6, using this relationship up here, times by P inverse. Now if we want to find this to the power 6, all we do is to raise each of the elements to the power 6. So we'll do 4 to the power 6 here, and then 1 to the power 6 here. So 4 to the power 6, just use my calculator to work that out. 4 to the power 6, that's 4096, and this one will stay as 1. So that will give us this calculation here once we've done D to the power 6. Now we can either work this out manually or use our calculators. I've used my calculator to get the answer for this. I should just be able to squeeze these numbers in, and I get 2731 here in the first element, and then 1365 here, and then 2730, and lastly 1366. So that is the value of a to the power 6 down here in the final part of B. So I'll just highlight my answers for part A as well, and I probably need to change where I've got these lines, because it makes it look like part B is all of that, and actually part B is this part here where I worked out P inverse and then did my working for part B in this section here. You should now be able to do exercise 5B on pages 176 to 179. So just a quick recap, we can diagonalize a matrix by working out a vector P, which is the matrix of the eigen vectors of our matrix A, and doing this calculation, and we'll just have the elements, non-zero elements along the leading diagonal, or if the inverse is difficult to work out, or we've been asked to use this form, then we can use the transpose of P. Remember, that's where you reverse the rows and columns, and P here will be the normalized eigenvectors. So here it's just the eigenvector matrix. Here it's the normalized eigenvector matrix, and you find normalized eigenvectors by dividing an eigenvector, or the elements in the eigenvector, by the length or modulus of the eigenvector. We would use this here. We did it in the last example where we need to work out a matrix to a power. Then we can perform this calculation here, because working out powers of a diagonal matrix is easy, because we just do powers to these diagonal elements here. We need to calculate P, which is going to be the same as doing this, the matrix of eigenvectors and its inverse, and we could either calculate that manually or use our calculator, and then we can work out the whole thing either manually or using our calculator.